είναι από τους σπουδαιότερους γεωτεχνικούς μηχανικούς του κόσμου και σίγουρα από τους σπουδαιότερους γεωτεχνικούς μηχανικούς της Ελλάδας. Ο σημερινός μας ομιλητής δεν θα μπορούσε να είναι εξαίρεση. Ο καθηγητής Kerry Rowe, στο Πανεπιστήμιο στον Καναδά, ο οποίος βρίσκεται σήμερα εδώ μαζί μας, για να μας δώσει μία διάλεξη πάνω σε ένα από τα πάρα πολλά αντικείμενα με τα οποία έχει ασχοληθεί. Ένα πάρα πολύ μεγάλο όνομα στον χώρο της γεωπεριβαλλοντικής μηχανικής, στον χώρο των γεωσυνθετικών, ένας άνθρωπος ο οποίος έχει τιμηθεί από δύο διαφορετικές διεθνείς ενώσεις με το να υπάρχει διάλεξη επωνόματί του. Υπάρχει διάλεξη Rowe από την ISSMGE για να τιμήσει τη συνεισφορά του στη γεωπεριβαλλοντική μηχανική και υπάρχει και διάλεξη Rowe από την IGS, την Διεθνή Εταιρεία Γεωσυνθετικών, για να τιμήσει την προσφορά του στο αντικείμενο των γεωσυνθετικών. Σήμερα μας μιλάει για ένα διαφορετικό αντικείμενο από τα πολλά για τα οποία έχει μιλήσει και με τα οποία έχει καταπιαστεί στη ζωή του. Και εγώ θα σταματήσω εδώ, δεν υπάρχει κανένας λόγος για περαιτέρω εισαγωγή από αυτή την υπέροχη διάλεξη που θα δούμε σήμερα και θα καλέσω τον ίδιο στο βήμα για τη 15η Αθηναϊκή Διάλεξη. Dear Kerry, the floor is yours to deliver the 15th Athenian Lecture on Geotechnical Engineering.
Well, thank you very much for what I'm sure were nice things you said, and also for your very kind hospitality during my last and current visit to Athens. I'd also like to thank the Hellenic Society for Soil Mechanics and Geotechnical Engineering for inviting me to present this 15th Athenian lecture. Looking at the previous lectures, I feel very honoured to be included amongst that group. Today, or tonight more specifically, I'm going to be telling you a story. And this story involves some challenges with old or new dams. But it's also a very personal story. It's a story of a boy who from the age of 5 wanted to build dams, and he secured his route to being able to do so. So we're going to start where I started in Australia. And in 1949, Australia began with a very ambitious scheme to direct the waters that fell on the Great Dividing Range, which runs, as you can see, as the black line, right the way up the east coast of Australia. And most of that rain in the blue area goes to the Pacific, and the purple area is very dry. So the idea was to divert water flowing in the Snowy River down to the Pacific to the west, where it could be used. And so here we see the first of two components to that scheme. The Murray scheme involved diverting water from Adaminobi Dam through to the Murray River in the west. The Tumut scheme diverted water from the Snowy River at Tantangra Dam and Adaminobi Dam to the west in the Tumut River. It was a very ambitious program, the most ambitious Australia had ever done, worth in today's dollars about $8 billion. It involved 7 power stations, 16 dams, 225 kilometres of tunnels. And at the time, the Australian population was about 8 million. And this project required 100,000 workers, 65% of them from 30 countries, but because of policies in Australia at the time, almost all of them from Europe. A lot from Greece, from Italy, from Germany, from the countries that had just been occupied by Russia to become part of the USSR, and from the UK. I'm going to end the talk with Snowy 2, which involves these 2 dams. Now, why is this particularly important to me? Because I grew up in the 1950s at the construction town where they were building Adaminobi Dam. I lived in this house. There's a picture of me when I'm about 5, a little older there. And as I said, I wanted to build dams from the first time I saw them being constructed. So if you want to build dams, you become a civil engineer. So I studied civil engineering at the University of Sydney. I graduated in 1974, and guess what? The Snowy Steam finished, and nobody wanted to build dams. Harry Poulos, who many of you will know, was my undergraduate thesis supervisor, and he persuaded me to do a PhD. And I studied many things in my PhD. I looked at soil structure interaction, anchors, piles and slopes. And in parallel, because I was working at the time, I worked on pile-socketed rock behaviour, driving piles into soft rock, rock mass modulus of weathered and jointed rock. Then I moved to Canada and started working on tunnels and geotextile reinforcement. And you probably look at that list as I would have 30 years ago and said, what's the relevance to tunnelling? Well, I eventually found they're all relevant to tunnelling. And I'll show you a little bit of that. 50% of my work since 1980 has been containing fluids, with natural materials, with geosynthetic materials. And they can play a very important role. They can be used in dams. And very dated now, ICOL survey from 2010 listed 264 dams where they were used. The majority embankment dams, such as you see on the left. But also geosynthetics are extensively used in the rehabilitation of dams, such as the concrete dam you see in the middle and the masonry dam you see on the right. Many different polymers have been used, but predominantly PVC, polyethylene, and bituminous. They can be left exposed or covered. The oldest exposed geomembrane is 50 years old, and the oldest covered 64 years. So they do last. So tonight, I'm going to talk about old and new dams, rehabilitation, and some of the roles geosynthetics can play. But we need to start with a little reflection on climate change, because it has a critical role to play in modern engineering of dams. And I hope I don't have to convince you that climate change is real. Temperatures, on average, keep going up. And nowhere are they going up faster than in the Canadian Arctic. Inuvik is part of the land of the midnight sun, but it was at 33 degrees a summer ago. Norman Wells is in the Arctic. A lot of it's on permafrost, and it was at 38 degrees last summer. Now, why does that matter? Because what happens in the Arctic doesn't stay in the Arctic. All of that melting water has multiple effects. And one of the greatest effects is actually going to be on Western Europe. Sea ice loss has many civil engineering implications. The rise in average temperature is what we talk about, but the really important thing is the increase in frequency of extreme events. Flooding of coastal communities is one example. It's only a couple of years ago that New York was flooded. Permafrost loss has a number of critical implications, not just for Canada and Russia where it's occurring, but for the rest of the world because of the methane that comes from that permafrost. And for Western Europe, it's the Gulf Stream. This is an unusual map. It has Europe superimposed on North America. Here is Edmonton in red and Sheffield in England in green. You can see they're at the same latitude, they're at the same altitude, but they do not have the same weather. We look at Edmonton's extremes, minus 45 to plus 38. Sheffield, minus 15 to plus 40. We look at the changes in average, and there's a 27.5 degree change in Edmonton and 18 in Sheffield. And all of that is because of the Gulf Stream. Well, here we are in Athens. which has not too dissimilar climate to Palo Alto. A little colder in the extremes, a little hotter in the extremes, but about the same average. We see a very different story if we compare Bordeaux, Genoa, Bucharest, and Kingston, where I live. Bordeaux and Genoa have about a 23, 22 degree spread and rarely go freezing. Bucharest and Kingston, interestingly, have a very similar spread. Bucharest's a little warmer, but very similar, which shows you very distinctly the effect of the Gulf. Now, why does this matter? Because the melting of Arctic ice is slowing down the Gulf Stream. And it is now the slowest it's been in 1,600 years. And the analysis is suggesting it's going to shut down. The only thing that's not known is it in 1 or 2 decades or 1 or 2 centuries. Time will tell. But climate change is not something to worry about in the future. It's here. March 24 was the warmest March in 175-year history. March 24 was the 10th consecutive month of record high global temperatures. And what are the implications? Well, I'm sure you're aware only too well, because we'll get to Greece in a moment, of the storm that caused the failure of Libyan dams, with thousands of losses of life and tens of thousands of people displaced. And people say, well, it's all because they didn't maintain their dams. Well, that may be a factor, but lots of parts of the world are not maintaining their dams, not just Libya. And look at the destruction that it reaped. Now we come to Greece. As you are only too well aware, a couple of weeks later, you had major flooding effects. And in the context of dams, what we're worried about in particular, how these floods will affect dams, because if they fail, the consequences are, as you saw in Libya, huge. And here is July 2024, a few months ago. Minnesota Dam, failure after flooding. Here's one a few months ago in Russia. Here is this month, hurricane twice hitting Florida. No dam failures, but you can see the havoc of climate change. So we need to mitigate the effects of climate change. And the first step towards mitigation is anticipating what are the extreme storm events. The second step is identify locations of greatest risk of flood. And by risk, I mean probability and consequence. Revise estimates of maximum probable floods. Reevaluate the safety of all dams in the context of the input design flood. And as needed, lower storage levels, raise dams, or increase emergency spillway capacity to accommodate the extra water that we now know is coming. Here is Lake Dunlop Dam. It was built around the time of the Great Depression in the United States. And let's look at this. That collapse was due to aging structural steel. So climate change is important, but it's only one of the factors that we need to consider. Other major factors are the aging of steel, the aging of concrete, an alkali aggregate reaction, clogging of filters, erosion of sediment in cracks or fractures, and time-dependent loss of soil strength. As I said, I'm a baby boomer. Huge amount of construction went on after World War II. And over the last 52 years, I'm not the only thing that's changed. Dams have been aging along with me, and that is becoming important. Just like humans, dams don't necessarily get better with aging. So we're going to now talk about rehabilitation, and then we'll talk about some new dams. So over the last 20 years, I've had the pleasure and privilege of working on 20 different dams, some of which I will discuss tonight. Now, the dams I'll be discussing in detail are predominantly from Ontario, and one I'll discuss in a lot of detail is from British Columbia. So I must thank Ontario Power Generation and BC Hydro for permission to talk about these cases. My role has been as a reviewer and advisor. Other people are doing all the hard work. And for the last 15 years, I've had the great pleasure of working with two giants in dam engineering, Carraherg and Joe Ehas, from whom I've learnt a great deal. And the privilege of working with many talented dam engineers with OPG, BC Hydro, and various consultants and a number of excellent contractors that I've had the privilege of working with. Having said all that, none of them are responsible for what I'm saying, except for me. So Ontario Power Generation has 66 hydroelectric stations, 240 dams on 24 river systems, and generates 42% of Ontario's power from hydro, out of a total of about 18.2 gigawatts. BC Hydro has 31 hydro stations and generates 12.2 gigawatts. So, clearly, dams are important from hydro. Why else are they important? Well, water supply. Flood control is a major consideration. And when you build a nice reservoir, it's lovely to have it for recreation. These are all great motives for building it. But they also induce great challenges as we try to deal with climate change and the increased severity of storm events. So what can we do if the input design flood goes up because of extreme events? Well, we could reduce operating water levels, but as you can see, that has very significant implications. Rarely is that an option. We can increase the dam height. That also has social and political effects. We can increase spillway capacity. And now we have to think very carefully about what is the risk of flooding as we increase the amount of water in a storm. So dams are a technical issue, but they're also political and social issues. And the engineer is often caught between the proverbial rock and hard place. But tonight, we're going to focus on the technical issues. So let's begin with the simplest when you can do it, and that is increase spillway capacity. So, what can we do when the input flood here exceeds the input design flood? Increase the capacity, and in this case, the flood risks were low. So, the capacity is going to be essentially increased by more than 50% by adding 4 new gates. Now, a lot of that is structural work, not of particular interest to the geotechnical side of the profession on which I sit, but there are some very interesting geotechnical issues with respect to, firstly, the cofferdam, but especially the upstream dam wall that was required to get the extra spillway capacity, because it's quite a complicated flow problem. And so here you can see a cross-section along the path of the upstream wall, showing the overburden and the bedrock. And this is the layout of the wall. You can see the drilled piles or caissons and the sheet pile walling between them. And this is what it looks like as a schematic that was prepared as part of a detailed 3-dimensional stress analysis to ensure that the system would be safe. We have socketed piles, we have anchors, and we have an interesting construction process. So here is the clearing up of the riprap where we need to place the piles. There are the forms that make sure that the piles are positioned correctly, starting at the cofferdam. The process of drilling out the soil, drilling out the rock, taking it away on a barge, filling it with steel and then concrete as the wall develops. And here we see it finished. A fascinating project. Let's move to another one. This is more geotechnical. Accommodating 1.5 metres of crest settlement. So this is a dam built on highly sensitive clay. We call it leader clay. It was built 60 years ago. And the engineers who built it were very good. And they made predictions of the settlement, and they predicted by this time it would settle 1.5 metres. And it has. They're really good. Two other things complicate life, though. The first is pore pressures. When you see 1.5 metres settlement, you know there's been pore pressure dissipation. But the excess pore pressures after 60 years are still 1 metre above the crest. That is because this clay collapses, it destructures, and it generates pore pressures as quickly as they dissipate. The second thing that couldn't have been anticipated 60 years ago is climate change and the effect that has on the input design flood, plus run-up, plus set-up. So that the core in 2018 was just 0.9 metres below the current IDF plus run-up and set-up. So what do you do? First obvious thing about is to increase the dam height. Well, look at those berms. Can you see how large those berms are in green out to the left and the right? That tells you the methods you had to go to keep this stable in the first place. And if we add 1 more metre of soil, this soil that is already challenged is going to be even more challenged. And you can appreciate that when I show you the shear strength profile. Now, the current factor of safety is okay, but look at that low shear strength you see around elevation between 78 and about 83 or 84. That is going to be a critical consideration. And in fact, it is one that says, no more adding 1 metre. So what can we do? Well, in this case, it turned out to be a relatively simple solution that you can't always use, but was rather fortunate given the other challenges. Because when you look at the 2018 IDF, it is about 0.74 metres below the crest. When you add the run-up, you are very close, as I pointed out, to the core crest. But with the Jersey barrier, one is able to accommodate just the current IDF run-up and set-up. So it deals with the wind and wave action. So that is the next example that I have. The third example is rehabilitation of a dam built on limestone. And this is a particularly sensitive dam. It's an Adirondack Dam built in 1957. It's on a mesa right next to Niagara Falls. And as you know, Niagara Falls lies between the United States and Canada. And this dam, as you can see in the diagram, has 2 generating stations and is located with a 20-metre high dam wall about 200 metres from the main crossing between Canada and the United States. So if something happens to that dam, billions and billions of dollars of trade have been wiped away, not to mention the lives of people living downstream. So needless to say, OPJ take it very seriously. Now let's have a look at its size. It's 300 hectares inside the dike, 7-kilometre long dike. It's a pumped storage scheme, the only one we have in Ontario, where you pump water in when you've got excess energy and you drain it out when you need that energy. And the water levels go up and down quite frequently. It has the advantage it's easy to drain. Now this is the dike. It's fairly traditional. We've got a base filter, sluiced rock fill, coarse filter, fine filter, compacted core, and then going out our filters, rock fill and riprap. And everything was very nice for a short while. It's on limestone, fractured limestone, high above the Niagara River. And 1 year after construction, there was a failure. Luckily, it was caught in time, not to be a severe failure, but nevertheless. Piping occurred through the overburden, through the fractures in the Lockport Formation, which is fractured limestone, and up into the zone outside the dam core. So this was fixed by grouting the affected area and by construction of a clay banking. So it's 1958. I'm still at Adaminaby Dam, still going to middle school. Now we come to 2011, and we have sinkholes developing. Sinkholes, when you have limestone, is a warning sign. We have leakage of 665,000 cubic metres per day, or about 7.7 cusecs. Because water is going down, it's migrating. So how do we fix this? Well, the first thing we could do is do grouting. Done it before, do it again, but it has obviously imperfections. So the grout curtain went in, but also there was a big debate, do we need to line the entire facility or just a portion of it? When ultimately the decision was made to do a portion. So we want to tie into the clay tongue, and we used geosynthetic clay liners to climb to the clay, and HDP as the lowest permeability component. So a GCL is, for those not familiar with it, a layer of bentonite sandwiched between two geotextiles. Bentonite is a swelling clay and can have, under the right circumstances, very low hydraulic conductivity. And so we're going to use this to tie in to that clay tongue that you can see on the left-hand side of the figure. And at the bottom of the figure, you can see the dike tongue coming out. You can see schematically we've excavated down to the dike tongue, and you can see it actually in the left-hand side of the figure. Then we place a GCL down, a geomembrane, another GCL, and gravel to bring it back up to an operating level. So here, the geosynthetic can be very useful in remediating the effects of aging on a hydraulic structure that was constructed more than 50 years ago. Liners don't always have to be continuous, just extensive enough to reduce the gradients to an acceptable level. And a combination of techniques often provides the most cost-effective solution. This was partially geomembrane GCL and grouting. So let me now move to my final remediation, and it illustrates the complexity of soil mechanics. So another dam constructed in 1957. I did mention there were a lot of dams built around that time. And at age 57, it had, shall we call it, its own version of heart failure, because we had a slide into the reservoir. So the slope movement was identified on the 26th of August, 2014. It is carefully surveillanced, and there was no sign of it the previous week before the failure. No deformations, no signs of creep, and yet, on that particular day, over a length of 65 metres, it dropped 1.7 metres. No further slope movements were detected. No history of slope movements. But a big red flag. You can see in the distance there the failure that's occurred. Here it is closer up. And again. And here, this is the panels there. And for those of you who know, Cora Herg is in the centre of the picture. You can see the drop. Now the big question is, why did this happen? And a university was hired and a couple of PhD students went away to try and solve the problem. And didn't quite solve it. Now I don't blame them, it's a very complicated problem. Lacustrine clay of high plasticity, smectite rich, expansive, strain softening, cemented by gypsum, and sensitive to the pore fluid, and fissured. Well, yes, life can be more complicated than that, but not often. For those of you who are devotees of soil mechanics, here are some of the properties. I'm not going to bore you by going through them, but to point out that there is a very significant difference between the peak and the residual. And the operating strength was ultimately backfigured to be in between. Here you can see some direct shear tests, and you can see the consequences and the slick and sided nature of the failure plane. Now, a lot of investigation went into this, A, because you want to understand it, and B, because a lot of other dams were built with exactly the same material at the same time. So you can see some location of boreholes here, and Canada has many disadvantages related to winter, but it has an advantage in that it's actually quite easy on thick ice to get out and drill, where otherwise you'd have to have a barge and it would be a lot more complicated. So we're going to look at some results at two sections, at section 2, where there was no failure, and section 3, where there was a failure, looking for signs or clues as to why it failed where it did. Okay, so here's a section that didn't fail. Fairly traditional core, filters, rock fill, clay foundation, silt and sand below that. Okay, not a lot of water, 6 metres. Doesn't sound a lot, but this is a very big reservoir, so if it fails, the consequences are huge. And here's the section that fails. So, what's the difference? Well, if you look at that, from most perspectives, you say this would be more stable. But it wasn't. So, in the end, what do? It wasn't practical to get out and remediate it from the lakeside, and so a new dam was built. And you can see here the cross-section through the dam with a cement bentonite positive cut-off going down the centre of the new structure. A lot of attention paid to filter blankets and drainage. And here is the old dam. Here is the start of the construction of the new dam as it evolves. This is preparing the material that will be adjacent to, on either side of the cement bentonite wall. It involved excavation down into the rock and excavation of the soil that had been placed to replace it with a cement bentonite slurry. And here you see the process in action. And the finished structure. And now the old dam is removed from above the low water line. And here is the total finished structure. Now, why that was particularly important, as I mentioned before, is not just for its own sake, but for many other dams that had been built with the same material at the same time. So, of course, what you would do is analyze those dams with the strength that was mobilized at the one that failed. And what you find is that in many cases, the factor of safety was too low. Here's one example where the calculated factor of safety was just below 0.9. Now, you could say, well, it should have failed. It hasn't yet. But if you went back to 2010, you'd say that other dam hadn't failed. And then it did. And so it's not very comfortable sitting with a factor of safety of 0.9 when you know the consequences of a failure could be huge. So what did OPG do? Obviously, got consultants to design and then contractors to install remedial measures. In this dam here, the downstream berm brings the factor of safety up to 1.5. Here's another example. Factor of safety of 1. Well, it's better than 0.9. Firstly, it was raised to 1.3 and others were raised to 1.3 and then went back and raised it to above 1.5. This one at 1.65. So this is a case showing the potential challenges that come with time with a dam that sat there happily getting tired, or more to the point, the soil below it getting tired. Let's now go to some new dams to finish off our talk. And we're going to start simple. It's always good to start simple. And this is a small dam, Sir Peter Sutherland Sr., located in eastern Ontario, a collaborative project with the local First Nations community. We have the creek called the New Post Creek, which will be dammed with an east dam, a west dam, and a spillway. We have an intake channel, 320 metres long, 8.5 metres deep, which will be lined with a high-density polyethylene geomembrane. We have a generating station, rather small, 28 megawatts. The overall cost was about 7.2 million euros per megawatt. And that water from the power station goes out into the Abitibi River. Here you can see a photograph of that. You see the power station, the penstock, the intake structure. And you can see a geotextile placed over the geomembrane, then a sand protection layer, an erosion protection layer, an ice and debris protection layer. Ice can be particularly problematic for dams in Canada. Now that was a simple one. And we've got quite a lot of time left, so you can anticipate the next one's not so simple. So this is Site C. It is a dam in British Columbia. This is an artist's impression of what it will look like. And it is the third dam on the Peace River. The first is the Bennett Dam, quite famous. Second is the Peace Canyon Dam. And the third is Site C. It's an earth dam, about 1 kilometre long, 60 metres high, The generating capacity is about 1.1 gigawatt, and the overall energy is 5,100 gigawatt hours per year. That's quite significant. This is a photograph taken when the project's almost completed, just before water storage. And this is a photo taken less than a month ago, after filling began. And another. So let's look at the various elements of this. Firstly, a diversion tunnel. It's got a capacity of 2,500 cusecs. Here's the intake structure, the tunnel, and the outflow structure. Then there's the earth dam itself. Fairly traditional, compacted, low permeability core, filters, rock. Here we have the spillway structure, roller compacted concrete, and the generating station, also roller compacted concrete. And here's the lined approach channel, where we'll be focusing a lot of our attention. Now, there were two areas of challenge on this program. Challenge one on the north side, on the left bank. Challenge two on the south side, or the right bank. Now, a newspaper article in July 2016, and this newspaper wasn't especially friendly to the project, stated, key geotechnical surprises to date include unexpected shearing during construction, unexpected slope failure on the project's north bank, a larger than expected deterioration of the shale bedrock exposed during construction, and a phenomenon called rock rebound swell. Well, here is the north or left bank after being stabilised. I don't have time to talk about that tonight. Here is the deep potential failure plain below the powerhouse that was mentioned, and we're going to dwell on that shortly. Then there was a deterioration of the shale bedrock when wet, and you can see here, and here, and here, it goes from being bedrock to gravel. And rock rebound, which we'll also touch upon towards the end. So there was a bedding plane known to be weak, and the initial plan that was being implemented was to put a shear key across that bedding plane. There's a thick concrete buttress you can see there. The key's going down 35 metres. And all was good until small movements were detected on a second bedding plane below the shear key. So, there are three issues that I just dwelt upon. One, the bedding plane. Two, the rock that doesn't like water. And three, rebound. And there was a two-part solution to these three problems. First, anchor the buttresses deeper into rock. Second, install 96 piles, each around 2.5 metres in diameter. That's fairly hefty. 37 millimetre thick steel filled with concrete, 50 to 60 metres long. Grouting of the bedrock beneath a plinth, and a sophisticated liner system to keep water away from the rock. So let's have a look at some of these. This is two of the piles that I just mentioned. Here you can see three of them at the bottom of that slope, just in front of the crane. And this is what they look like before they go in. You get a sense of scale from that 6 foot high, approximately, let's say 1.8 metre high man standing in front. and looking down the barrel, and you can see the steel is thick. Now let's talk about the lined approach channel. Now I've turned the drawing you just saw 90 degrees so that you can appreciate the next few diagrams, which are also rotated in the way I've shown here. So now the concrete is at the top and the lined approach town below it. So here is the roller compacted concrete, and our liner system has 3 regions. Region 1, Region 2, Region 3. And here is a cross-section, and you can see that Region 1 extends about 50 metres from the concrete, the most critical zone. Then we have Region 2, and then in the least critical zone, Region 3, each with a somewhat different liner system. So let's start with the simplest one, Region 3, about 4.3 hectares. And one of the design considerations is minimal erosion. So there's rock fill, cobbles and gravel to provide that. I will not dwell on that in other cross-sections. Minimal leakage. So how do we get minimal leakage? A geosynthetic clay liner. Now we need to protect the clay liner from gravel, so we have 0.3 metre of sand protection layer. Now when the dam is full, it'll have somewhere around 28 metres of water above this location, and the GCL is probably going to be about 0.0, about 7 millimetres thick, 0.7 of a centimetre. So you can appreciate that we're dealing with a very large gradient of the order of 4,000. And a large gradient like that can induce internal erosion of the bentonite. So an important consideration is preventing internal erosion. So we have a 0.3 metre compacted till layer here, 25 to 65% fines. And although it has a not insignificant hydraulic conductivity, that's not why it's there. It's there to prevent internal erosion of the GCL. Now that's all well and good if we could wish the dam into place. But a critical part of engineering, especially with geosynthetics, is thinking about what can happen to your materials between the time you place them and the time they go into service, because that can be critical to their long-term performance. Now in this case here, we anticipated it would have to go through 2 winters before the dam was filled. Now in that period of time, what happens to a GCL? Bentonite loves water, and it'll suck up water from wherever it can get it. That compacted till has water, so it will suck up water from the compacted till. That compacted till, because it's a natural material in this part of the world, is going to have a lot of calcium and magnesium in it. Yet we have a sodium bentonite. That creates what's called cation exchange. And that is important because it reduces the swelling capacity of the GCL. That would not matter if we weren't going to leave it for a couple of years before the water came. But what will happen in a couple of years? Winter and summer. Winter, freeze thaw. Summer, wet dry. Now bentonite has a capacity to self-heal very well when it's sodium bentonite. But if it's had a lot of cation exchange, it loses that swelling capacity and the capacity to self-heal from those cracks. And so its operational hydraulic conductivity would be not what we want it to be. So what do we do? Of course, the first thing is to recognize what I just told you. The second is to put in a 300mm coating as part of the GCL. So by putting that coating down, it prevents hydration of the GCL from the compacted till. It also substantially improves its hydraulic resistance, but that's not why it's there. It's there to protect the GCL from cation exchange. And here's the GCL. You can see the cover geotextile. You can see the bentonite on the right. It's been removed on the left. You can see the carrier geotextile with its 300-gram coating. And that is region 3. Region 2 looks much the same so far. It has a GCL, same story. Geomembrane, though, has been added. So now we want even less water to get through. 3.5mm thick PVC. Sand protection layer, but also now a 2,000-gram geotextile. And because we want to find holes in the PVC, we have a thin conductive sheet. And we've got the compacted till and the coating for the same reasons as before. Now let's move to region 1. 2.5 hectares, but wow, what a 2.5 hectares of liner. Here we have gravelly sand, and liner type 1, which is going to need a whole slide to itself. 100mm mud slab, 300mm of concrete aggregate, and another mud slab with drainage from that layer. And here we see the construction of a liner system that has to withstand 25mm of potential horizontal movement of the underlying bedrock. So here we've got the mud slab, a geotextile, a tertiary geomembrane, another protection geotextile, concrete aggregate, mud slab, geotextile. This is a PTFE, very thin friction resistance, so it provides very low friction resistance layer. A polypropylene reinforcing geotextile, a 2mm PVC geomembrane, a geocomposite drain, a thin conductive sheet, a 3.5mm PVC, and a geotextile protection layer before we get to the sand. So let's look at some of these materials. This is the geotextile, and by testing we demonstrated this particular geotextile, and most do not have this, had 100 years design life at operating temperature. This is the low friction material, the reinforcing geotextile, quite a strong one, and here is the PVC. And again, work by J.P. Giroux supported a 100-year design life at operating temperature. This is a geocomposite drain. Products can look identical and have totally different service lives. I'm going to show you results for the component that affects their service life. And the magic number is we'd like to be at about 100. Look at this product. Totally unacceptable. This one, pretty good, relatively speaking. If you didn't do that type of testing, you'd have no idea, and your material, if you picked number 1, would degrade before your 100-year service life, substantially before. So remember, people do what you inspect, not what you expect. So we now have quite a complicated liner system that can accommodate, at least in theory, 25mm of horizontal movement. But do we test it? Yes. So here is a test with a 50mm wide. We only require 25, but 50. 100mm deep crack, loaded to 1.5 times its design pressure to 430 kilopascals, and the residual deformation was about 10mm at the top and the woven geotextile did its work, at about 15 millimetres at the bottom. So it performed well with twice the design gap and 150% of the design load. The last detail is the connection to the concrete. And quite a connection it is. There's the geotextile, the slip layer, the reinforcing geotextile, the PVC geomembrane, the geocomposite drain, which terminates before the dip down, the upper geomembrane, all tied together and tied into the wall. And this is designed to withstand 100 millimetres of vertical or horizontal movement. It was this detail that drove the use of PVC. So there it is. Here's region 2 being constructed. You see the compacted till, the GCL, the conductive film, the geomembrane, and the geotextile. So difficult situations can be dealt with using many different geosynthetic components. Geomembranes, geonets, geotextiles, reinforcements, slip layers, conductive layers, and GCLs. But I caution you again, products can look the same and actually have very different service lives. Choose wisely. If you don't have the expertise, get it. Remember, people do what you inspect, not what you expect. So this is bringing me full circle to finish off on Snowy 2.0. It is the next generation of power for Australia, and it's using 2 of the dams from Snowy 1.0, and the idea is when you have excess wind and solar power to use it to pump water from Talbingo Dam up into Tantangra Dam. And then when you need the power, you run it the other way. It has to be completed before a number of wind projects come online and 5 coal power stations are going to be closed. It's expected to be operational at the end of 2028 and hopefully with power by 2027. But like many projects involving dams, it's had its problems. It started with 1 tunnelling machine, which was stuck for 19 months in soft rock near Tantangra. They now have 3 tunnel boring machines. Its original budget was $2 billion. That had risen to 6 by 2017, 12 by 2024, and I predict higher by 2028. But it's still very, very cost effective at 3.4 million euros per megawatt. So new hydro projects have been challenging anywhere in the world. The most common problem is over-optimism. Wishful thinking can be our biggest enemy. And I thank you for your attention.
Dear Kerry, thank you very much for tonight's lecture. Η διάλεξη αυτή ήταν υπέροχη. We want to express our gratitude not only with a vote of thanks by our audience, but also with the plaque we have for you for the opportunity of delivering the 15th Athenian lecture as the Athenian lecture of tonight's jubilee of almost 25 years since the beginning. Thank you very much for tonight's lecture, and I will ask our audience again to deliver a vote of thanks.
Thank you very much. Thank you.